According to Wikipedia, the free encyclopedia, the first known approximation of the inverse golden ratio by a decimal fraction, stated as about 0.618034, was written in 1597 by Michael Maestlin of the University of Tübingen in a letter to his former student Johannes Kepler. So the question is, notwithstanding the shortcomings of the period, could Euclid have known or had any notion of the value of the inverse golden ratio? Using Euclid's well-founded method of just compass and ruler, I shall demonstrate that the answer is a resounding yes. Draw a line. Replicate the line, set it at right angles in the centre of the first line. Replicate the line, set it at right angles in the centre of the second line. Replicate the line, set it at right angles in the centre of the third line. Join the four vertices to form a square. Having halved the four internal lines, we can assign a value of 1 to each of the 8 parts. We have four right-angled triangles CAB of area 2 times 1 divided by 2 equals 1 square unit, plus a 1 by 1 square of 1 square unit. Therefore C squared equals 5 square units, and C squared equals 2 squared plus 1 squared, so C equals root 5. The graphic we have produced is a proof for the Pythagoras Theorem, and substantiated in The Ascent of Man by Jacob Bronowski, and God Invented the Integers edited by Stephen Hawking. We can rotate the internal square until its sides are parallel to those of the outer square. Labelling the larger side of the rectangle A and smaller side B, so that the outer square is now A plus B all squared and inner square A minus B all squared, we get the equation A plus B all squared minus A minus B all squared equals 4AB. These are different valued A and B's than those of the triangle. This is a theorem in Euclid's Elements, Book 2, Proposition 8, and demoted to the quarter squares rule by the mathematical fraternity because, in my opinion, it is an embarrassment to them in their denial of a simple proof of Fermat's last theorem. So could Euclid have deduced that the rectangle was anything special? Well, yes. Definition 4 of Book 6 of his Elements states, a straight line is said to be divided in extreme and mean ratio when the whole is to the greater segment as the greater segment is to the less. Hence 1. PR divided by PQ is equal to PQ divided by QR. Let PQ equals 1, then 2. PR equals 1 divided by QR, and 3. PR times QR equals 1. 4. 1 plus QR times QR equals 1. Therefore, QR squared plus QR minus 1 equals 0, a quadratic. From the diagram, A plus B is equal to A minus B plus 2B. Therefore, B equals A plus B minus A minus B, all divided by 2. A plus B equals root 5, and A minus B equals 1. Therefore, B equals root 5 minus 1, all divided by 2, which is equal to 0.61803398875. Now PR is equal to 1 plus QR, and QR equals B, and 1.6180339 times 0.6180339 does indeed equal 1, as the numbers and equalities predict. I was aware that 5 squared, 5 to the 4th, 5 to the 6th could be expressed as the sum of two squares, the number of expressions increasing with the increase of the exponent, and only one of which was coprime, and the others composite. Ignoring composites, I have discovered intuitively that every power of a Fermat 4n+1 prime can be expressed as the sum of two squares, and that, in principle at least, the two base numbers are easily derived, no matter how large, without resort to anything other than simple arithmetic. Since all odd integers, and therefore all powers of Fermat 4n+1 primes, can be expressed as the difference of two squares, we can generate a coprime Pythagorean quadruple for them all. A coprime Pythagorean quadruple with one term negative can be generated for all powers greater than 2, such as 11 squared equals 10 squared plus 5 squared minus 2 squared. Tables for sums of two squares are given for 5, 13, 17, 29, including a negative Pythagorean quadruple for each. The sums of squares for the powers of the Fermat primes are obtained by infinite ascent, by taking the sums of two squares for the prime P1 equals a squared plus b squared and splitting into a times b plus b times a equals x. X will be one of the base numbers of p squared, so the second base number will be obtained from y equals the square root of p squared minus x squared, giving p squared equals x squared plus y squared. A and b become constant multipliers for all the powers, so the first base number for pq is obtained from either a times x plus b times y or from a times y plus b times x. One gives the base number for the next higher power, and the other is p times a multiple of a preceding base number, but which gives what is random, as is whether the output is the smaller or larger of the two base numbers, but this is not a hindrance. The second base number for PQ is obtained as per 17. See tables. How do we obtain the sum of two squares for the Fermat prime in the first place? From the Fermat-Bateman triangle, or the sum of two squares, of course. This is, however, impractical for increasingly large primes. Some thoughts on the golden ratio. What if we had made the side of the centre square 2, 3, 4, 5 or more? From the quadratic QR squared plus QR minus x equals 0, for x equals 1, 2, 3, 4 and 5, we get the recorded values. The numbers 5, 12, 21, 32, 45 are obtained by feeding x into the quadratic equation as was done for 1. These numbers are just the partial sums of 5 plus 7 equals 12, plus 9 equals 21, plus 11 equals 32, and so on and so forth. All have the property that x plus a decimal times the decimal equals x, and also that x plus the decimal divided by the decimal is equal to x plus 1 plus the decimal. That is, they all increase by 1. Finally, could Euclid have known the precise value of the inverse golden ratio? Yes.